Today we're going to talk about double angle identities. Okay, so here are all of our double angle identities that we're going to be using. So for sine, cosine, and tangent. And then notice for cosine you actually have a couple different options. So you can either use this formula that you see here, this one, or this one, and they will all give you the exact same answer for cosine. Okay. So very quickly, I want to show you how we can actually come up with these identities from the sum and difference formulas that we learned about yesterday. Okay, so if you recall, remember we learned about the sum and difference identities. Okay, so if we start with these and we manipulate them a little bit, we can actually derive our double angle identities from them. Okay, so one quick example, if I have the sum identity for sine that says if I take two angles, they're different angles, I add them together, I just use this identity. So instead of using a different angle, so instead of using V, let's say I have two of the exact same angle. So what if it was U plus U? So two of the exact same angle. So basically everywhere that there is a V, I'm going to replace that with a U, okay? So here and here, both of those V's, I'll replace them with U's instead and rewrite my formula. So I have the sine of U times the cosine of U plus the cosine of U times the sine of U, okay? Now, since I'm using the exact same angle, whatever that is, it's the same thing, I could rewrite this U plus U as the sine of 2U, okay? Or a double angle, and that's what I see here for this double angle identity. I'm just multiplying whatever angle it is that I'm working with by 2. I'm doubling that angle. All right, funny enough, this term and this term are exactly the same, even though they're flip-flopped around. I can reverse them, like I could write this instead as sine U times cosine U, because the order we multiply things in doesn't matter. I can flip that around. So these are actually both the same term. If I add those together, that would make two of the same terms. So there's 2 times sine of U times cosine of U. Okay? So that's where we get that first double angle identity from. Okay? All right, so now let's actually put some of these into practice. We're going to find the following exact values using the double angle identity formulas. So some of this is going to seem a little bit silly because if you're looking at the cosine of 60 degrees, you might be thinking, hey, like I can easily find that on the unit circle, right? Like I just go to 60 degrees, I know that angle is on the unit circle, and I look at the x value, because cosine is the x value. So if I did that right now, I went to 60 degrees, the x value is 1/2. Great, I already found the answer, that's it. Now, the reason we're going to go through this whole double angle process might seem a little silly with these first two problems. It'll become a little bit more clear with this last problem, but really a lot of this won't hit home until you get to calculus, and then you're using these double angle identities more usefully, okay? For now, we definitely know the answer is 1/2, so you can use that to check your answer, right? But I want to walk you through the process of actually just going through and plugging everything into these double angle identities and getting comfortable with using them. So when you get to calculus and you're using them then, it feels a little bit more familiar, okay? So even though we know the answer is 1/2, let's go through the process of using this double angle identity, okay? So the first thing I need to do is take this angle that I'm given, and I need to figure out how to rewrite this so that it's 2 times some angle. Okay, so how could I rewrite 60 as 2 multiplied by some angle? So hopefully you're seeing that if I could rewrite that as the cosine of 2 times 30. okay? Because 2 times 30 definitely makes 60. So that's how I could rewrite that 60-degree angle to be a double angle. All right, so then I'm going to go through and everywhere that I see this theta, this placeholder, and just to clarify, I used a different placeholder than they're using. It doesn't really matter. They used theta for the angle, and we used u over here, but there's not a difference. It's just a different notation that we're using, or different placeholder. So everywhere that there's a theta, I'm now going to replace that with 30. So let's go ahead and write this. So I have the cosine squared of 30 degrees minus the sine squared of 30 degrees, okay? Now, remember how I said that for cosine, you get a lot of options. You can use any of those three formulas. So I could have as easily used these other two, and you will still get the same answer if you try to use those other two formulas. All right, so then how do I work with this? How do I simplify something like this? Okay, so the first thing that I'm actually going to do is find the value of the cosine of 30 degrees. Okay, so I'm going to go to the unit circle and find the cosine of 30 degrees, which is root 3 divided by 2. So that's the cosine at 30 degrees. And then since this is cosine squared, I'm just going to take this value and square this entire thing. Okay, so that's how this is going to work if it's squared. Same thing for sine, so then I'll go and find the sine at 30 degrees, and that should be 1/2. So I'm doing 1/2, and since this is squared as well, I'm going to square the 1/2. Okay, so then if I'm simplifying this down, that exponent of 2, remember I have to distribute to both the numerator and the denominator, so this gets distributed here and here, okay? So then the square root of 3 squared, well the square root and the square cancel each other out, so then it's just 3 as in the numerator. And then 2 squared would be 4. So I get 3/4 from that, from distributing that exponent of 2 to both the numerator and the denominator. And then here, if I'm distributing it here, I would have, well, 1 times 1 is 1, and then 2 squared is 4, okay? So 3/4 minus 1/4 gives me 1/2, which is what I was expecting to get anyways, right? So there's my answer of 1/2, just walking you through how you would use one of those double angle identities to get that same answer, okay? We'll do one more of these, but now with the tangent, okay, of pi divided by 3. So what you could do, again, like I've talked about before, is you could definitely convert this to degrees if that's easier for you to work with. Feel free. But I'm going to encourage you to work with this in radians during this video, okay? So again, I try to think of anything in radians when I see it as just a fraction without the pi there. So I think of this as 1/3. So how could I rewrite 1/3? How could I rewrite 1/3 so that it's 2 times something gives me 1/3 or pi thirds? So that would actually be 1/6 or pi over 6. If I took pi over 6 and I multiplied this by 2, that would give me pi over 3, which makes sense in degrees, right? Like if I had 30 degrees, if I multiply that by 2, I get 60 degrees, okay? So I just want you to see how we can do that in radians as well. So 2 times pi, actually let me use a different color there. So 2 times pi divided by 6, that would be the same thing. That's another way to write pi divided by 3. All right, so then I'll go into my tangent formula. And I'll write this as 2 times tangent of pi divided by 6 all over 1 minus tangent squared also of pi divided by 6. Okay, so now that I have all of that plugged in, we can start simplifying that down. So then I need to find the tangent of pi over 6. You can use that unit circle that I showed you in the last video that already has all the tangent values calculated. But also we remember that tangent is just my y value divided by my x value. So the tangent at pi over 6 is going to be 1/2 divided by root 3 divided by 2, and then I take this and I flip and I multiply it. So those cancel and I get 1. 1's in the numerator. 1 is in the numerator over root 3. Remember, I have to rationalize this. So if I rationalize it, I'm multiplying this by root 3 divided by another root 3. That's going to give me root 3. And then I know that both of those together, if there's 2 of them together, that's root 3 squared. Square roots cancel out, and I'm just left with 3. So that tangent value should be the square root of 3 divided by 3. Okay, so then I'm going to get 2 times root 3 divided by 3, because that's what I got to replace the tangent of pi over x with, is root 3 divided by 3, all over 1 minus root 3 divided by 3, and remember that is squared. Okay, so then we just have to do all the work of simplifying this down. So I can go ahead and write the numerator. Well, I know that there's a 1 underneath this 2 here, so if I multiply straight across, I'm just going to get 2 root 3 all over 3, so I can combine that together, okay? I just multiply those together. The next part here, I'm distributing that exponent of 2, so that's going to give me 1 minus 3 all over 9, okay? So remember that cancels out that square root there, and 3 squared is 9. Okay, and then in the denominator, I can go ahead and simplify that a little bit further. So let me actually rewrite this here. How on earth could I subtract these? Okay, so remember, I can only subtract if they have the same denominator, if these fractions have the same denominator. So I'm going to need to rewrite this 1 as a fancy 1, okay? So if I rewrite this 1 as 9 divided by 9, that's still the same thing as 1, then I'll be able to perform that subtraction, okay? So I'll get 2 root 3 divided by 3 all over, well, 9 minus 3 is 6, so 6 divided by 9, okay? All right, so now that I have all of this simplified in the numerator and in the denominator, I can go ahead and multiply by the reciprocal, okay? So I'm going to take this, flip it upside down, so I'll have 9 in the numerator, 6 in the denominator, and instead of dividing, I'm going to be multiplying, okay? All right, so if I multiply this, I'm going to get 18 root 3 divided by 18. So we can easily see that those 18s cancel each other out, so that I'm only left with the value of root 3. That is my final answer, okay? So we can double check this, right? Like if we go to the tangent of pi divided by 3 and find that really easily in the unit circle, is that root 3. Okay, remember the tangent is just y divided by x, so that would be root 3 divided by 2 all over 1/2. Flip this around and multiply it. And yep, I definitely see that the answer is root 3. So I did everything correct when I was using my double angle identities. All right, the last problem we'll look at, we're going to find the exact values of sine, cosine, and tangent using double angles, okay? So first, let's kind of stop and analyze this problem that we're given. So we're told the cosine of some angle. We actually don't know the angle this time. So before, we actually had a value for what that angle is. This time, it is a mystery, okay? but that is equal to negative 2 divided by 3. And then they mention this right here. What does this mean exactly? Well, this is just saying that that angle, whatever that angle is, it's in between pi divided by 2 and pi, okay? So I'm actually going to look at that on the unit circle right now. Where is pi divided by 2 and where is pi on the unit circle? So pi divided by 2 is right there, and pi is here. So our angle is somewhere in between these two values, okay? Well, another way to say this is that our angle is somewhere in which quadrant? Which quadrant would this be? So hopefully you recognize this as quadrant 2, okay? So that's basically what they're saying when they're using this notation here, is that our angle is located in quadrant 2. So if they're talking about a quadrant, that's actually going to lead me to draw a picture of that quadrant. So I'll just do a rough sketch. So I know that angle is somewhere in here. And then hopefully this is kind of leading you on a little bit to think about a problem that we had back in Unit 10, okay? So I'm going to go ahead and draw a triangle. So hopefully this is getting a little familiar to you from Unit 10. I'll draw a triangle in quadrant 2. And then this angle here would be angle U. I don't know what that is right now. But then I'm told that the cosine of that is negative 2 divided by 3. So I can actually take these values and put them on the triangle in this quadrant. So this would be, remember, my adjacent and my hypotenuse. So in this triangle, 2 would go here and 3 would go here. And then where would the negative go? Okay, so remember that hypotenuse is never going to be negative. So that negative needs to go with the 2, which makes sense because it's going in the negative x direction, okay? And then the last thing I can do to help me out with this problem is using the Pythagorean theorem, I can find the value of this missing side. So that would be at 9 minus 4, take the square root of that, so I get the square root of 5 if I'm using the Pythagorean theorem. All right, so I have this problem completely set up. I've dissected everything that they've told me about here. Now let's find the sine of 2u, double of what that angle is. So I'll go up to my identity. That's the identity I'm using. So 2 times sine of that angle, and then times the cosine of that angle. All right, so how am I calculating this? So funny enough, I'm going to actually go to this triangle that I created, and this is where I can substitute in some of these values, okay? So I can find the sine of 2u by actually going to the triangle and finding the sine of that angle. So here, the sine of that triangle would be opposite over hypotenuse, okay? So I can take the sine of u, I know that's going to be opposite over hypotenuse in that triangle, so I can replace that with the square root of 5 divided by 3, okay? And then the cosine of u, I already know what that is just from the beginning of this problem. The cosine of u is negative 2 divided by 3, and I can verify that in the triangle, so I can replace this with negative 2 divided by 3. All right, and then all I'm doing from here is just simplifying all of this down. So here I can think about this 2 with a 1 underneath it, so I'm just multiplying all the numerators straight across. So 2 times square root of 5 times negative 2 gives me negative 4 square root of 5. And then 1 times 3 gives me 9. All right, so that would be my double angle for sine. All right, let's go ahead and do that for cosine and tangent. And at this point, I encourage you to pause the video, try and see if you can find these on your own, and then you can check back in to see if you have the correct answer. So I'm actually going to, just for fun, use a different identity here than this last one that we used. So let's say I was going to use this 1 minus 2 sine squared. Okay. So I can bring down the 1, bring down the 2, and then the sine from this triangle we just found a second ago would be the square root of 5 divided by 3. So I have the square root of 5 divided by 3, and then all of that is squared, because remember that angle, that sine is squared. So I've just substituted that in, and then now I'm just simplifying. So to distribute that exponent of 2, I get 1 minus 2 times 5 divided by 9. Okay, so remember that has a 1 underneath it, so if I multiply those together, I'm going to get 10 divided by 9. So 1 minus 10 divided by 9. And I can change this 1 to be a 9 over 9. So then my fully simplified answer would be negative 1/9. Okay, and then the very last problem, where we're finding the tangent. Okay, so I have 2 times tangent of that angle all over 1 minus the tangent squared of that angle. So the tangent of this angle would be opposite over adjacent, so that would be the square root of 5 divided by negative 2. And then that is all over 1 minus the square root of 5 divided by negative 2, and all of that is squared, because this is tangent squared. And then I just have to do the job of simplifying this down, okay? So in the numerator, I could put a 1 underneath this, multiply straight across, and I get 2 square root of 5 all over negative 2. Really, those 2's can cancel out, right? So I could write this, actually, as negative square root of 5. Okay, I can just cancel out the 2's. The negative is still there, so I'll just bring that up with the square root of 5. So that's what the numerator looks like. And then in the denominator, okay, let's say we distribute the exponent of 2, so I would get 1 minus 5 all over 4, okay, because negative 2 times negative 2 is positive 4. And then I can change that 1 to be 4 over 4. And simplifying that, I get negative 1/4. All right, everything is completely simplified, and I can go ahead and multiply by the reciprocal. So if I take this, flip it upside down, so I'm multiplying this by 4 over negative 1. Well, I know a negative and a negative make a positive, and then this would just be 4 square roots of 5. Okay, so that 4 and the 5, they're both in the numerator, they would multiply, and a negative and a negative would make a positive. So that's how you would find the exact values for sine, cosine, and tangent using double angles for this problem.